So, Robert, we've been looking at how to write good functions and how they connect together. But if functions are the bricks, what are the blueprints?
Precisely. Well, classes are the blueprints, defining the overall structure of your program, like organizing and managing a whole house, instead of just a single room.
Great. So, clean code at a class level. How does that differ from clean functions?
It's similar but broader. Functions are like individual rooms, each with its purpose. Classes are like the entire house, with rooms, utilities, and overall architectural style.
What are some common missteps?
Lots of small, unorganized classes. Spaghetti code, you know? Classes that do way too much, the God class.
So, a single class that handles all aspects of the application?
Exactly. Or classes that are way too specialized. A class just to hold a single value, for instance.
So, how do we avoid those?
Encapsulation, abstraction, inheritance, composition. You know, thinking about how to organize data and responsibilities within a class.
Could you give me a concrete example?
Imagine an e-commerce app. A product class, with attributes like name, price, and ID. Separate classes for orders and customers.
Makes sense. And why are these different classes helpful?
It breaks the problem down. Easier to maintain, add features, or fix bugs. It's all about code organization.
So, the bigger picture. Classes make code easier to reuse?
Absolutely, if designed well. Classes form the framework.
Thanks, Robert. That makes perfect sense.
My pleasure.
Robert, you mentioned encapsulation is a crucial part of clean code. But sometimes, tests seem to require access to things that should be hidden. How do we balance these competing needs?
Exactly. Encapsulation is fantastic for maintainability. Imagine a big system where everything's public. It becomes a spaghetti mess. But tests need to interact with private parts for unit testing. We always prioritize the ability to write tests.
So it's a trade-off?
A calculated trade-off. We make the part protected, so it's restricted. This is a last resort. We look first to see if there's a way to maintain the privacy. But testability is often paramount.
Like a secret agent. You want to be able to test your code thoroughly.
Exactly. You want your code to be robust. Making variables or utilities protected makes testing simpler and more comprehensive.
But how do we decide when it's okay to make a part protected and not just public?
If it's a test in the same package or module, we don't hesitate to make it accessible. But if it is for the public use, we try to maintain the separation of concerns in our code, and that's really important to keep maintainability high.
You mean it depends on the context?
Absolutely. It's about understanding the scope. If only a handful of other parts of the system need access, maybe a protected or package-level access is sufficient, without completely opening up the interface.
That makes sense. Can you give a real-world example of this happening?
Sure. Imagine you're building a database library. Internal functions to manage connections might be encapsulated, but test functions are given access to internal data to test the entire library interaction.
That's a good example. So, prioritize testability inside the module/package, but minimize outside access.
Exactly. We want to be able to fully test our code.
So, it's not a blanket rule, but rather a careful evaluation based on the context.
Precisely. It's all about the careful consideration of accessibility.
Thanks, Robert, that clarifies things.
You're welcome, Andrew.
So, Robert, we've been talking about clean code, and it seems like modularity is key. But what about this concept of single responsibility principle?
Absolutely. It's a fundamental principle in object-oriented design. Imagine a class responsible for everything about a dashboard, including versioning and UI elements.
Yeah, that sounds messy.
Exactly. That class has two reasons to change: the dashboard's display and its versioning. The SRP says each class should have only one.
So, splitting it up?
Precisely. We isolate the versioning logic into a separate class, like a version class.
But why is that better?
Imagine upgrading the UI. You only have to touch the dashboard class. If you need to change the versioning, you only need to touch the version class. That makes it easier to update or debug each aspect of the code in isolation.
Makes sense, but won't lots of tiny classes create a lot of complexity?
It's a common concern. But a system with many well-defined small classes isn't more complex. It's more organized. Think of a toolbox, lots of little drawers, each with specific tools. Easier to find the right screwdriver than one big box, right?
That's a good analogy. So, is there a practical example of how this has improved code quality?
Sure. In my last project, we had a massive class controlling user accounts, order processing, and payment systems. We reorganized it based on SRP. We created dedicated classes for accounts, orders, and payments. This greatly reduced bugs because we were able to test and maintain each piece independently.
Massive Timeserver.
That sounds like a lot more manageable.
Much more so. The key is identifying those different responsibilities and cleanly separating them.
Makes me want to go and start refactoring my code now.
Always a good time for that. Start small. Gradually, your code becomes cleaner and more maintainable over time.
Thanks, Robert. That's very helpful.
You're welcome. The SRP is about making your code a more manageable tool.
Hey, Robert. Thanks for joining us today. We've been talking about writing clean code, and now we're diving into cohesion. Can you explain what that means in terms of class design?
Sure, Andrew. Cohesion, in the context of object-oriented design, is about how closely related the methods and variables within a class are. A highly cohesive class is one where all the methods primarily work with the same set of variables.
So, the more methods that use a single variable, the better?
Well, ideally, yes. Imagine a class with all its methods working together on a shared purpose. It's like a well-oiled machine. But maximal cohesion can be tough to achieve in practice.
Right, makes sense. But what are some examples of when cohesion might be a problem, and how would you recognize it?
A class with many methods manipulating different sets of variables, potentially performing completely unrelated tasks, is a problem. Imagine a class that manages user accounts, but it also does data validation for orders. Those two things probably belong in different classes, right?
So, it's about avoiding those mixed responsibilities?
Exactly. A real-world example is a large order processing system. If a single class handles everything from order creation to shipping, that class is probably not cohesive, leading to complexity and potentially bugs.
That makes total sense. So, you're saying for good design, you want things to be neatly organized in terms of the variables that are used together?
Precisely. Classes with well-defined responsibilities are more maintainable and easier to reason about. Sometimes, refactoring is needed to separate and improve cohesion.
I see. How do we identify where to split up a class to improve cohesion?
Look for methods that aren't using many of the variables in the class. That's a strong sign that the class is too broad and should be broken down.
That's super helpful. Thanks for sharing.
My pleasure.
Hey Robert, this refactoring thing sounds cool. Can you give me a real-world example? Like, imagine a spreadsheet function that calculates everything. How would you approach breaking it down?
Sure, Andrew. Think of a super complex spreadsheet formula. It's one giant block of code, doing everything. It's probably a maintenance nightmare. You'd want to identify the different logical units. Maybe one part calculates sales figures, another discounts, and a third formatting.
So you just split it up?
Exactly. You break down those sections into separate functions, then classes.
What about the variables that are used to cross those different sections?
You might move those to instance variables within classes. This keeps the functions related to a single class more focused.
So cohesion?
Yeah, cohesion is about having a tight relationship between class methods and variables.
So that's how you get rid of spaghetti code?
Precisely. This refactored print primes example is a great illustration. It takes a massive block of code and makes it more organized. This refactoring, while maybe longer initially, makes the program easier to maintain over time.
But wouldn't it take longer?
Yes, there's a cost, but think of it like building a house. Building it piece by piece might take more time initially, but it's more resilient and easier to maintain over time.
Ah, I see. So it's about long-term maintainability.
Exactly, and testing after each small change ensures your program's behavior remains correct.
What about tools for refactoring?
There are IDEs with refactoring tools.
Wow, that makes sense. Thanks, Robert.
You're welcome, Andrew. Let's keep this conversation going.
Cool. Can you tell me about specific tools for doing this?
IDEs, like IntelliJ Eclipse, often have refactor tools. They allow you to move code, extract methods, and change variables. Some even automate parts.
What kind of testing is required? Unit tests?
Absolutely, Andrew. You need to make sure each refactored function or class is performing as expected.
It's like building a car piece by piece. You need to check that each part works before you assemble it.
Exactly, Andrew. You can't build a car with faulty engine.
So you break it down and then test each piece?
Yes. You break it down into units, test each unit, then put them together. That's how you ensure that the complex program still does what it's supposed to.
Right. I get it now. Hey, Robert, we've been talking about object-oriented design, and you mentioned something crucial last time, coupling. Can you elaborate on how isolating dependencies from change impacts the overall quality of the code?
Absolutely, Andrew. You know, tightly coupled code is like a house of cards. One small change in the external API can bring down the whole structure. The dependency inversion principle, or DIP, is a fundamental design pattern that tackles that problem head-on.
So, how does DIP work?
We use interfaces. Imagine you have a portfolio class that depends on an external stock exchange. DIP tells us to abstract that dependency instead of directly using the concrete stock exchange class. You create a stock exchange interface that defines the actions you need. Then, the portfolio class uses this interface.
Gotcha. But why is this better?
It makes your code far more flexible and testable. Instead of writing tests that depend on the constantly changing stock exchange, you create a mock version of stock exchange, our stub for testing purposes. This allows for isolation.
I see. It's like having a substitute in a football team.
Yep, exactly. You don't need the actual team. You have a functional substitute for testing purposes.
Okay, that's a very helpful analogy. But can you give me a real-world example?
Imagine building a payment gateway. It would rely on many services, maybe even different payment processors. The dependency on those details should be isolated via interfaces.
So, that's great, but what's the potential downside?
It adds complexity and can be overhead for simple things, but when things grow in size, the DIP is invaluable.
Interesting. So, when should we not use it?
When dealing with simple use cases or internal components, you'll often find it might increase complexity for no gain.
That's really helpful. Thanks, Robert.